Hello there. Today I'm going to do a little walkthrough of the magnetic fields topic for AQA. It's in the fields section, not electromagnetic induction. That can maybe form another video, but this is just an introduction to this topic, how it's taught for the AQA course. Lots of the stuff will be similar for other specifications, but there is a little bit of divergence in this topic depending on the exam board. So, first of all, to start off talking about fields and the effect of magnetic fields on objects, on magnetic materials. One thing I notice over the years is that the diagram that they want students to draw at Key Stage 3 quite often doesn't always reflect exactly what the field looks like, really. I think this particular image here is a bit more realistic on the left, and it looks a bit more similar to the one on the right. But generally at A-level we're not tending to draw things like this. This is more of a GCSE diagram, really, but generally it's good to recap what the field looks like for a bar magnet, and with the field lines going north to south, essentially. Then a little bit about north-seeking and south-seeking poles, a bit of a recap of GCSE and Key Stage 3. Then the law of magnetism: like poles repel, unlike poles attract. Often at this stage, both GCSE and A-level, I talk about the Earth. And, oh yeah, one thing that's important here, in the convention in electric fields was that the field direction would be the path taken by a positive charge. And for magnetic fields, it's sometimes helpful to say, the field lines would be the path that a small free north pole would take. Not that such a thing exists, of course. You can't get a monopole. Now, the Earth's magnetic field, this isn't really on the course, but I think it's just of interest. Why does the north of a compass point geographically northwards? And so both the GCSE and A-level, I talk a little bit about the Earth's magnetic field, and that really in the northern hemisphere, off northern Canada, because it wanders quite a lot, there is a south magnetic pole, and that's why the north of a compass points towards the north. It doesn't point to the geographic North Pole because it's not in the same place. But and this has changed throughout history, and you could go into a bit of hinterland here about how we know why it's changed, looking at ancient lava flows and things like that. But anyway, I digress. I won't talk too much more about that because it's not really on the specification or anything like that. But some students might ask, and you could also talk about compasses, that you have to have a different compass in the northern hemisphere compared to the southern hemisphere, because there's a little bit of a weighted end on the compass so it doesn't drag, and it's in the opposite place in the other hemisphere. So the first important thing really is looking at the right hand grip rule. So sometimes you've got to predict the current direction, or you've got to say give the field direction, and the right hand grip rule is really used, or right hand thumb rule or screw rule is really useful for this. And either establish the direction of the field, or it can decide the current direction, essentially. And it comes up again later on. Really useful. Really important to sort of get through to students what rule you need for various things. They've all the Fleming's left hand rule. You've got the right hand grip rule. In the AQA course, we don't tend to do the right hand generator rule particularly, but I know it appears in other courses that. And the conventional current here we're talking about, it only becomes important when we look at BQV in terms of what direction the electrons are actually going in. So, motor effect is, again, something they should have covered, the students, at GCSE to some extent. And a classic demonstration there with a major magnet. You can often see then the wire will jump in and out of the jaws depending on the direction of the current and the position of the poles. And you can use Fleming's left-hand rule to dictate which direction it's going to go in. So we'll have to do a little bit more on Fleming's left-hand rule after this slide, I think. So the size of the force, the size of the kick that you get in the motor effect depends on the strength of the magnet, the strength of the magnetic current, the length of the wire in the magnetic field, and then the angle between the field lines and the current. And it's really important to emphasize that the force is greatest when the current is perpendicular to the magnetic field and zero when it's parallel to the field, which will be important in the understanding of a motor later on. So Fleming's left-hand rule lots of teachers got lots of different opinions about how you get students to remember it. I've found over the years that FBI is really good because there's no room for getting this wrong. There's no sort of, I forget the word I'm looking for now, but there's no room for getting this wrong in terms of confusing some of the letters. So F, force for the thumb, then B and I. So B, the flux density and of magnetic field direction, and I being the current. So left hand FBI, you could sort of exaggerate that a little bit and lessen. It's quite memorable, and I think that's better than some of the older ways of doing it myself. But it's up to the teachers how they want to teach it. But I know that there can be confusion over what the M stands for and things like that. Is it motion? Is it magnetic field? In some of the other ways of learning it. So each to their own. So students, depending on what background they've had, if they're doing the AQA course at A-level, maybe they did AQA GCSE, where this equation I think is in that. Our students don't do AQA GCSE, so they won't have come across B before up until this stage. So F equals Bill, really important equation. So the force on a current carrying wire in a magnetic field. You could have sine theta for this if it was an angle, but the assumption is that the current is perpendicular to the magnetic field in the modern course. I think they used to have in the previous specification Bill sine theta, I think. So I being the current, L the length of the wire in the field, and B the flux density. So a new unit for some students if they haven't done the AQA GCSE before. A Tesla there. So if you rearrange that, B is F over IL, so 1 Tesla would be 1 Newton per amp per meter, or Tesla being force per unit, force per amp per meter. And so that could come up in definitions in two different ways, really, there. Okay, so that's worth taking a little bit of time to take that on board. And also worth emphasizing that generally you don't get huge values of Teslas. And you can see there just inside, even with an MRI magnet, you probably get a couple of Tesla. But generally we're going to be talking about milli-Tesla in a lot of the physics questions, essentially. So in a neutron star, they're 10 to the 8, but that's quite the exception. All the others would be much smaller than that. Even a fridge magnet might be just, a couple of tens of milli-Tesla. And there are other units, obviously, in America that use Gauss more often than Tesla. Now, in terms of motors, I think it's important to see as many moving motors as possible. This particular slide is obviously not really animated there, and it's talking about the force on length X and length Y, and the forces are opposite because the currents are in opposite directions. Worth emphasizing that the line from X to Y and the equivalent parallel line beneath it won't experience any force because it's parallel to the field. But I've just made a note there of O Physics and Walter Fendt. Those websites got really good simulations of or animations of motors. O Physics and Walter Fendt, great websites. The Fendt website's really old. The O Physics one a bit newer, but they've got really good things to recommend. Both of those things, really, just to show that the motor turns around via the middle. In terms of the practicalities, in lots of GCSE courses, they have to know about the brush contact and the split ring commutator. But again, the animations are really good for showing how the split ring commutator works. I think over the years, you get a lot of initial questions about how that works. There's a really good video clip on Adam Hart Davis where he talks about the first electric motor by Sturgeon, and in one of those clips, it's available on YouTube in one of those compilations. And Sturgeon's motor, and he goes into a pub and he shows a version of Sturgeon's motor and the commutator's really neat in that demonstration, so that's a nice little video clip to see. But the split ring commutator is there to change the polarity of the current every half turn, otherwise it wouldn't continue to turn all the way around. And a bit of momentum also helps, and the brush contacts, the carbon brush contacts there to make sure that the circuit is connected to the rest of the motor at all times. But yeah, I think over the years there's sometimes not a great understanding of students of how the commutator works, the split ring commutator. So an animation says more than 1,000 words really in terms of explaining how it works. Now when we're looking at that stage, then we're looking, up until now, we're looking at current flowing through a wire, but this can be more generalized to charged particles in magnetic fields, and this is pretty much the only area in the AQA course where the conventional current, you need to put that aside and think about what the electrons are doing, or other charged particles. So charged particles experiencing a force in a magnetic field, and there's charged particles in a current. So there's a little bit here about they mentioned some uses of this in cathode ray tubes and old-fashioned scopes like that, and to old TVs. But there's plenty more uses coming up. Talks here about the topics being a bit back to front. It doesn't really matter which way around you do it, whether you do F equals Bill first or F equals Bev. Probably, I think I prefer to do F equals Bill first, but these charges are just, the electrons are inside the wire, so we could do it either way really. And you can go from, I think it's better starting with Bill because you can derive Bev from it. So I say Bev, BQV is technically the equation, but F equals Bev is generally the case because it's usually an electron, not always though. So if you substitute in Q equals IT into F equals Bill, you can get F equals BQV, which is a more general equation, so it's not just applying to electric current flowing in a wire. It could be any charges could be protons, could be alpha particles, that kind of thing. Really important equation, but often F equals Bev because often it's electrons in questions. Now direction is important at this stage, okay, and I'm going to take a little bit of look at that now in a second. First of all, we need to look about what path the particles go in. So when we did electric fields, we found that if electrons are going at right angles to an electric field, then they move in a parabola. But in this case, they're going to be moving in a circle, and we'll find out how that is in this. It's not really an animation, but a stepped PowerPoint slide. So you've got an electron gun there with some electrons coming out, and the magnetic field is coming out of the page. And the conventional current would be in the opposite direction, which is important to really emphasize. And so if you use Fleming's left-hand rule, the force is to the left. And then a short time later, that electron will have veered off to the left somewhat, and then the force is further down to the southwest, and so on. And if this keeps happening, then you get circular motion. The force being perpendicular to the velocity causes the path to constantly change, and so you get circular motion. So for magnetic fields, charged particles move with circular motion. Really important slide that for understanding. So, as it says there, we often look to equate circular motion equations with field equations, in this, like we did in gravitational fields. So now we're going to equate F equals Bev with F equals mv squared over r for circular motion, and then we derive the radius of curvature equation, which is given in the formula booklet in at least one section. I can't remember, I haven't got it on to hand, but sometimes I think it's in the turning points perhaps, and the magnetic fields, or at least it's in the turning points section. I think maybe that's the way around it is. Important the students are not clear with their language here about the radius of curvature, so the path becomes more curved, r is reduced, and things like that, because it's easy to trip up in the language there. Worth noting that the charge to mass ratio, or the specific charge, is kind of hidden inside that equation. If students do turning points in physics, this comes up again. One of the main reasons why, in our case, we do turning points in physics at the moment is because of covering a lot of ground in the core again and in greater depth. And quite a few things that are coming up here come up in turning points again later on. Just a little aside here that so while electrons move opposite to the conventional current, if you see a proton or an alpha particle, positively charged particles, then they will move in the same direction as the conventional current would be. So just careful with the Fleming's left-hand rule. Also, the Hall effect isn't on the AQA course. It's in things like WJC, and I'm sure it's probably in some of the other courses. Definitely worth watching the clip, the 60 Symbols YouTube clip about the Hall effect, because it's a very good video. And also, I think it's good to just teach beyond the course, because a lot of instruments rely on the Hall effect. I think 3 Nobel Prizes have been given out about the explanation of the Hall effect. So I think it would be remiss maybe not to mention it at this stage, even though it's not technically on the AQA course. So applications then, the main applications of magnetic fields will be the cyclotron and the mass spectrometer, but a bit about cathode ray tubes here, thermionic emission, that kind of thing. Thermionic emission comes up a lot in turning points in physics at the root of all of the electron tubes, that are used there in that topic. But it's mentioned here a little bit. So at this stage, because we do turning points, I don't talk about it in huge detail. But obviously, if you did astrophysics or one of the other options, it's worth talking about thermionic emission in detail here. Mass spectrometers, I don't know, I haven't checked, but I think it feels like more than half the questions that come up. Even though cyclotron, in the specification for AQA, it mentions cyclotrons as a use of magnetic fields, but then it doesn't mention mass spectrometers. But I think at least half the questions come up on mass spectrometers, and they come in. There's three kind of areas you need to know about. And maybe I'll flick forward a little bit to this one. So you've got the ionization chamber, then you've got the velocity, then you've got a bit of acceleration going on there between plates, and then you've got, so it's 4 chambers, sorry, and then you've got the velocity selector and then a final chamber. So let me just go back and have a look at the velocity selector. So a really clever component that allows you to get constant speed charged particles going through. So first of all, those charged particles have been ionized in the first chamber, otherwise you can't accelerate them if they were neutral, and then they're accelerated by another pre-chamber, just electric field. But then they come into the velocity selector and they are exposed to an electric field and a magnetic field. The magnetic field in the case on the board here is coming out of the page, like a dart going towards you, you'd see a dot and the outer sleeve, and then if it was going into the page, you'd see the crosshairs of the back of a dart or something like that. It's the way we remember that. So in this case, the electric field is going upwards, F equals EQ, and then you've got F equals BQV, then acting downwards. And particles that have got the same velocity, well, particles where the forces are balanced will go through, and they'll have just a single velocity, and that velocity will be the electric field strength over the flux density, the magnetic flux density. Nice little derivation of that there. And so the velocity selector is great, and it does, again, it comes up a lot, this kind of process in turning points in physics. So then the third chamber there, depending on the size of the charge, you get different radius of curvature. So it's worth emphasizing that's just a magnetic field in the final chamber that's got the detector in. And in exam questions, sometimes students, they work out the radius of curvature, and I think they forget to multiply by 2 when they're trying to work out a distance in a chamber. So that's something that's worth highlighting. Sometimes there's a factor of 2 missing from answers, which is a shame because they've done all the hard work till that point. Just a common slip up because they've worked out R and they needed the diameter. Now there's quite an old mass spectrometer there, but lots of the good universities have got mass spectrometer departments within them, often within chemistry, and researchers can send unknown samples in and they can have it analyzed. Really useful device. Cyclotrons, in terms of particle accelerators, there was a question on a synchrotron with AQA a few years ago, but generally they'd be on cyclotrons. So there's a cyclotron there at a university, I think, and they accelerate particles, and they've got loads of different uses, medical uses, as well as sort of just purely research. Better than a linear accelerator because you can it takes up less space and you can keep accelerating quite a lot. I sometimes at this point show the Stanford linear accelerator and how the size of it is still there. If you go on Google Maps in San Francisco, you can show students just how large a Stanford linear accelerator was, and this can do all of that and perhaps more depending on how strong the magnetic field is in just a small space. And then it just leads into discussions about circular accelerators then, although this isn't strictly circular, and it isn't strictly spiral either, really. So that you've got 2D electrodes there, you've got magnetic field at right angles to the movement of the charged particle, and it could be any of a number of charged particles in there. Now I don't think here it's not obvious there that when the charged particles go between the Ds, they're exposed to the electric field the electric field then accelerates them, but the particles are going straight there. So this is why, whilst it looks like a spiral there, it isn't really. It's a barred spiral, I guess. So the particles go straight, and then they've been accelerated by this electric field here, and then they go in circular motion because they're experiencing a magnetic force then within the d electrodes. And so there's a really good simulation for this online. I'll have to try and remember to put the link in the description, as well as this PowerPoint, but where you can change various parameters and see what happens in terms of how tight a barred spiral you get. Really useful devices, and made a lot of difference in research in medicine over the years. Because it's going faster, the particle, as it's been accelerated, then you get a larger circle then as a result. But we need to emphasize that the electric field is accelerating in between the Ds, and then this magnetic field within the Ds then. In the Ds, sorry, themselves. So R equals mv over bq again there. And then just looking there at the time for one revolution. Oops. And that's the end of that topic then, really. Lots at this stage. I do a big compendium of questions about applications, just to make sure that students understand that. Maybe I could put that in the description as well, maybe. But that's the sort of halfway through the magnetic fields topic. Then I'll try and produce a video on electromagnetic induction at some stage. But I hope you enjoyed that little quick tour or recap, maybe if you're a student going through that. This bit, I think students generally find it pretty okay. I think the electromagnetic induction part, students can find the theory quite heavy going, although the questions that come up tend to be okay, I think, in the electromagnetic, the EM induction topic. Okay, thanks for listening.